Welcome to a definitive exploration of one of the most profound minds in modern physics. This presentation, titled The Architect of Quantum Symmetry, delves into the extraordinary life, foundational mathematical formulations, and enduring engineering legacies of Eugene P. Wigner. As a towering figure in theoretical physics, Wigner fundamentally reshaped our understanding of the universe by pioneering the application of group theory to quantum mechanics. Through this deep dive, we trace his journey from profound mathematical insights to his practical contributions in nuclear engineering. Join us as we uncover the story of a visionary whose structural frameworks continue to guide the cutting edge of quantum science today. We now explore the remarkable duality of Eugene Wigner, truly the master of two worlds. On the left, we see him as the abstract theorist. A 1963 Nobel laureate, Wigner pioneered the use of group theory, becoming the architect of symmetry in quantum mechanics, enabling the prediction of the invisible laws of nature. On the right stands the pragmatic engineer. Originally trained as a chemical engineer, Wigner became the world's first true nuclear engineer. He translated abstract ideas into physical reality, designing the massive 100-megawatt Hanford plutonium production reactors. Ultimately, Wigner seamlessly bridged these two realms, using abstract symmetry to predict the invisible and chemical engineering to build the unprecedented. Next, we trace the origins of an extraordinary intellectual cohort. Born in 1902 to a middle-class family in Pest, Austria-Hungary, Eugene Wigner's genius was nurtured at the elite Fazori Evangelicus Gymnasium from 1915 to 1919. There, he studied under the legendary mathematics teacher Laszlo Ratz. Political turmoil soon followed. In 1919, Wigner's family briefly fled the communist regime of Bela Kun, leading to an anti-communist conversion to Lutheranism. Crucially, Wigner came of age alongside a staggering group of Hungarian prodigies known as the Martians of Budapest. This legendary inner circle included his brilliant high school classmate John von Neumann, as well as future scientific giants Edward Teller and Leo Szilard. This brings us to a fascinating chapter titled Chemical Engineering by Day, Quantum Physics by Night. To satisfy his practical-minded father, Wigner spent his days at the Technische Hochschule Berlin, earning his doctorate in 1925 under the eminent physical chemist Michael Polanyi. Yet, his nights belonged to the University of Berlin. Here, Wigner immersed himself in theoretical physics, attending the legendary Wednesday colloquia alongside titans like Albert Einstein, Max Planck, Werner Heisenberg, and Wolfgang Pauli. This period forced a pragmatic compromise, forging a uniquely versatile mind. Wigner emerged fluent in both the grueling logistics of industrial heat transfer and the highly abstract realms of quantum theory, a dual expertise that would soon change the world. We now arrive at a critical breakthrough, curing the Gruppenpest, group plague. Early quantum physicists faced a massive problem, making sense of highly complex, chaotic atomic spectra. The solution came when Wigner, prompted by John von Neumann, introduced a symmetry filter. He applied group theory to quantum mechanics, mapping physical symmetries directly to quantum states. However, they faced heavy resistance. The physics community initially rejected this abstract math, mockingly calling it the Gruppenpest. But the triumph was absolute. Wigner's landmark 1931 book ultimately forced the scientific world to accept symmetry not just as a tool, but as a foundational law of nature. Next, we examine the mathematical architecture of particles, in which Wigner laid the bedrock of modern particle physics. First, Wigner's theorem, 1931, proved that physical symmetries, such as rotations, translations, and parity, must be mathematically represented on a Hilbert space. They operate strictly as either linear or antilinear operators. Building on this, his Poincare group classification, 1939, analyzed the inhomogeneous Lorentz group. Wigner proved a profound truth. All elementary particles in the universe are fundamentally defined by just two invariant characteristics, mass and spin, or helicity for massless particles. Through these dual breakthroughs, Wigner established the foundational mathematical framework that would eventually become the standard model of particle physics. We move forward to a series of monumental breakthroughs in defining the architecture of matter. Wigner's insights continuously mapped the microworld, beginning with Wigner correlation energy, where he calculated the electrostatic energy contribution arising from electrons avoiding each other due to Coulomb repulsion. This led to the prediction of the Wigner crystal, 1934. He theorized that at ultra-low temperatures and densities, electrons would cease acting like a gas and freeze into a highly ordered, three-dimensional solid lattice. Finally, we see the Bright-Wigner formula, 1936. Co-developed by Wigner, this became the definitive mathematical formula for resonance, calculating the exact probability of an atomic nucleus capturing a slow neutron, a critical pillar of the future of nuclear physics. We now arrive at a critical geopolitical turning point, the catalyst for the atomic age, August 1939. The threat materialized in 1938 when German scientists discovered nuclear fission. Having fled European totalitarianism, Wigner was terrified of a Nazi atomic monopoly, famously noting that thoughts of being murdered focus your mind wonderfully. This fear drove the intervention. On August 2, 1939, Wigner and Leo Szilard drove to Long Island to meet with Albert Einstein. The result of that historic meeting changed the course of human history. Together, they drafted the famous Einstein-Szilard letter to President Roosevelt. This crucial document directly prompted the creation of the Uranium Committee and ultimately gave rise to the Manhattan Project. Next, we look at the engineering masterclass of designing the Hanford production reactors. A major debate arose over reactor cooling. The helium proposal absorbed very few neutrons, but it would run dangerously hot and require overly complex metallurgy. Instead, the Wigner solution, water, was approved. It leveraged a water-cooled design operating at 100 megawatts of power, utilizing 200 tons of uranium and 1,200 tons of graphite moderator. While water absorbed more neutrons and threatened to corrode the uranium, it promised faster construction and much safer operating temperatures. During the execution, Wigner's team brilliantly engineered solutions to overcome corrosion and neutron loss. Wigner personally reviewed every single DuPont blueprint, ensuring that absolute theoretical perfection successfully met industrial reality. We now examine two critical phenomena, the Wigner effect and the Windscale fire. Wigner predicted that radiation could fundamentally alter solid materials through a three-step atomic process. First, during impact, a fast neutron from nuclear fission strikes a carbon atom within the solid graphite moderator. This causes a displacement, knocking the atom out of its lattice site to create a vacancy and an interstitial atom trapped in a metastable state, a Frankel defect. Over time, this results in stored energy, creating a massive buildup of potential energy that can trigger a sudden exothermic recombination if heated unexpectedly. This prediction met a tragic real-world consequence in 1957, when stored Wigner energy was unexpectedly released, causing a massive fire at the Windscale military reactor in the United Kingdom. We now review a catalog of eponymous breakthroughs, summarizing Eugene Wigner's astonishing scientific versatility across 2 decades. In 1931, he laid the groundwork for quantum math with Wigner's theorem, mapping symmetry transformations to unitary or anti-unitary operators. By 1934, he shifted to solid-state physics, predicting the Wigner crystal through the crystallization of an electron gas at ultra-low densities. In 1936, He co-developed the Bright-Wigner formula in nuclear physics to calculate neutron capture cross-sections. By 1939, he defined the core of relativistic physics with the Wigner classification, identifying elementary particles by mass and spin. Finally, in 1946, his focus on materials engineering led to the Wigner effect, which describes atomic displacements that cause stored potential energy. We now consider the confronting paradox of the conscious observer, a mind-bending thought experiment known as Wigner's friend. Inside the lab, a friend measures a quantum spin system, collapsing its superposition into a definite state of 0 or 1. However, standing outside the lab, Wigner hasn't seen the result. According to strict quantum mechanics, he must model the entire laboratory, including his conscious friend, as existing in an entangled quantum superposition. This leads to a profound implication. 1961. Wigner argued that this thought experiment exposed a fundamental truth. It is impossible to formulate the laws of quantum mechanics in a fully consistent way without explicitly referencing human consciousness, thereby forever linking the physical universe to the observing mind. We now ponder a philosophical wonder, a miracle bordering on the mysterious. Here, we examine Wigner's famous 1960 thesis, The Unreasonable Effectiveness of Mathematics in the Natural Sciences. On the left sits abstract mathematical invention, born purely from human logic, beauty, and aesthetics. On the right lies empirical physical reality, governed by nature, matter, and experimental data. Wigner observed a staggering truth. Concepts invented by mathematicians with no practical intent routinely turn out, decades later, to perfectly describe the exact rules of the physical universe. As he beautifully summarized, the profound appropriateness of mathematical language for formulating the laws of physics is a wonderful gift that we neither understand nor deserve. We conclude our journey by looking at Wigner as the pragmatic realist. Haunted by his youth fleeing totalitarian regimes, Wigner held a deep, lifelong commitment to defending open societies. On the left, we see him as director of Clinton Labs, 1946, where he managed the facility that became Oak Ridge National Laboratory, focused on reactor technology training, and oversaw the first massive shipments of medical radioisotopes. On the right, we see him as a civil defense advocate, 1960s. Directing Project Harbor. Rejecting mutual assured destruction, Wigner argued that allocating 10% of the defense budget to blast shelters was morally and strategically superior to pure offensive deterrence, showcasing a mind fiercely dedicated to practical human survival. We conclude our exploration by examining the profound legacy of Eugene Wigner. His contributions fundamentally shaped modern science, earning him the prestigious 1963 Nobel Prize in Physics alongside Maria Goeppert-Mayer and J. Hans D. Jensen. Wigner was recognized specifically for his foundational contributions to the theory of the atomic nucleus and elementary particles, particularly through his discovery and application of fundamental symmetry principles. Wigner's unique brilliance lay in his ability to exist seamlessly in two worlds. He was a visionary abstract theorist who uncovered the invisible geometric laws of reality, yet simultaneously a pragmatic nuclear engineer who built tangible foundations for the atomic age. His dual legacy remains a testament to the ultimate unity of pure thought and practical creation.